So for the next number of lessons, I'm going to be talking about kinetics. Now, chemical kinetics is the area of chemistry in which we're concerned with the speed of a reaction. So up until this point, we've been talking about how much of a product is produced, but what we're now going to talk about is how quickly a reaction occurs. And there are four main factors that affect the speed of a chemical reaction. The first one is the physical state of the reactants. Specifically, the more readily reactants collide with one another, the faster the reaction is. So keeping this in mind, molecules that are in the aqueous or the gaseous states are going to react much more quickly than molecules that are in the solid state. Now, if you do have molecules that are in the solid state, you want to maximize surface area, and you actually do this on a daily basis by chewing. By chewing, you're breaking apart molecules, which then can be exposed to a larger amount of all of the different enzymes that are going to break down your food. If you just swallowed your food, then it would take a lot more time for those reactions to occur. The second factor that affects reaction rate is the reactant concentration. Specifically, the more reactant you have, the greater its concentration, the greater the number of collisions are going to be, and therefore the faster the reaction is going to be. Remember, you want as many collisions as possible to increase the rate of reaction. The third factor that affects reaction rate is reaction temperature. Now, this is very similar to the point I just made, but as your temperature increases, your kinetic energy increases. So not only are you going to have more frequent collisions like in number 2, but you're also going to have collisions with greater energy, which means that the rate of reaction is going to increase. And finally, the presence of a catalyst is going to increase the rate of reaction, but catalysts themselves are not used up. So we'll look at catalysts in more detail later on in this big idea.
So we just discussed different factors that affect the reaction rate. So we talked about the physical state of the reactants, the reactant concentration, the temperature, and the presence of a catalyst. Well, how exactly do we measure reaction rate? Well, reaction rate simply is a measure of the change in concentration over time. So how much does the concentration change over a given amount of time? And specifically, something that interests us is as a reaction proceeds, what happens to its rate? So if you look at this example here with this graph, notice it shows at the very beginning at time equals 0, the concentration of your reactant is 0.10. And as this graph proceeds, if you notice, based on our definition of reaction rate, the slope of this curve represents the rate, the reaction rate for this reaction. Because notice it is the change in concentration, y, over time, x, right? Rise over run. So notice as this reaction proceeds, the reaction rate decreases. Well, why is that? Well, it makes sense now because as we had just stated, if your reactant concentration decreases, that means that your rate is going to decrease because there are going to be fewer collisions and therefore the rate's going to decrease. Well, as your reaction proceeds, if you notice, your concentration of C4H9Cl is going to decrease. Therefore, there are going to be fewer collisions, and therefore your rate is going to decrease as well as the reaction proceeds. Now, I'm going to hint at a topic that we haven't started yet, which is equilibrium. All right, well, as my C4H9Cl and my H2O react, producing my products, which are C4H9OH and HCl, as that reaction proceeds, remember that you will also have the reverse reaction starting to occur as well. So what is the rate for that reaction? Well, at the very, very, very beginning, right when C4H9Cl, your reactant, and H2O start to react, you don't have any of your products. And so it is possible for your reaction rate to start off as 0. So your reaction rate for the reverse reaction is going to start off as 0. Then, as you increase the amount of products you have, which, because it's a reverse reaction, will actually serve as the reactants, as you get more and more products, the rate of the reverse reaction is going to increase. And it's going to increase until you reach equilibrium. And remember equilibrium from last year, which, again, we're going to cover in grueling detail this year. But remember, equilibrium is the point at which the rate of your forward reaction equals the rate of your reverse reaction. So you start off with a high rate for your forward reaction, no rate for your reverse reaction since you have no product, and then the forward reaction slowly slows down, your reverse reaction slowly speeds up until they end up equaling each other.
So let's actually look at reaction rates and how we can use our stoichiometry in order to determine reaction rates. Well, in this reaction here, the rate of disappearance of A is going to be the negative 1 over A, the little a being its coefficient, times its rate, equals negative 1 over B times the rate of B, equals 1 over C times the rate of C, which equals 1 over D times the rate of D. So this is how we use stoichiometry in order to determine the rate. So let's look at an example. It says, what are the relationships between the rates? Well, I know that negative 1/2 of the rate of N2O5 is going to be equal to 1/4 of the rate of NO2, and that's going to be equal to simply the rate of O2, okay? Now, the reason, why exactly does this matter? Why do we care about this stoichiometric relationship for reaction rates? Well, if I know the rate of one of them, I can actually determine stoichiometrically the rate of another. So here it tells me that my rate of disappearance of N2O5 is 4.2 times 10 to the negative 7th. What is the rate of appearance? And so what I can do is multiply that 4.2 times 10 to the negative 7th by negative 1/2, and I'm going to set that equal to 1/4 times the rate of NO2. And then all I have to do is solve for the rate of NO2 by multiplying both sides by 4, and I get 8.4 times 10 to the negative 7th. Notice I made the 4.2 negative, and that's because it's the rate of disappearance, making sure that the rate of NO2's appearance is positive. So the rate of something disappearing is negative, the rate of something appearing is positive.